Okay, let's get into some of this radical chemistry here. So far, we've already covered quite a bit. The basics about that you need to know to understand radical chemistry. And a lot of parallels, like the stability of radicals, definitely parallels what we saw for carbocations. And they're both electron poor. We've introduced the basic elementary steps of radicals, and now we're going to see it applied. This section is all about free radical halogenation of alkanes. So this reaction is pretty important because alkanes, the generic formula being C sub n H2 sub n plus 2, they just really don't do much. You can add electrophiles, you can add nucleophiles, and nothing's going to happen. About the only thing they do is burn. And that is in itself an extremely important reaction because it pretty much powers our entire planet. But we're not going to talk about that. We're going to talk about making alkanes synthetically useful. And that means taking a boring, inert alkane that doesn't react with electrophiles or nucleophiles and converting it into an alkyl halide, which, as we know, is a nice reactive electrophile that can, in fact, undergo quite a few reactions. For example, substitution at this carbon or elimination by removal of a beta hydrogen. So, this is a synthetically valuable reaction to know. Mechanistically, it's a chain reaction, which means a little goes a long way, if you know what I mean. Once you have initiated the reaction by forming some radicals where once there were none, you're off and running. So the initiation step gets you started, and then those radicals can do all kinds of things. The propagation steps are reaction steps where there's no net loss or gain of radicals. So they just keep the reaction going. And then every once in a while, two radicals will combine to terminate the reaction. So a termination step removes your reactive species by quenching the radicals and ending up on the product side with no radicals. Okay, so it's really important to understand this mechanism because it pretty much lays the groundwork for the rest of the chapter. So the initiation step is right here. Bromine has a sufficiently weak bond that a little light or a little heat, you got bromine radicals. No radicals on the left, two radicals on the right, makes it initiation. What does that bromine radical do? Well, this is a pattern we're going to see throughout chapter 25. The Br radical, bromine radical, is looking for something to hook up with, and it is going to undergo a hydrogen atom abstraction. When it abstracts that hydrogen atom, you end up with a radical on your alkane. So here is where the selectivity comes in. Which hydrogen is abstracted? Well, in this case, there's only one kind of hydrogen, so there's only one radical that can possibly form. The alkane radical, the alkyl radical, then can react with your stoichiometric reagent. So I want to emphasize that there's one equivalent, at least, of Br2 to react with your alkyl radical. So, alkyl radical, again, looking for something to hook up with. What's it going to run into? Well, most likely it's going to run into the bromine. So what do we have here? We have a propagation step here, and we're going to have a propagation step here because one radical on this side and one radical on this side, because when it reacts with the bromine, we're left behind with Br dot as well. So, initiation, two different kinds of propagation steps, and then termination. Well, how does this reaction end? Well, one way it ends, of course, is when the bromine is consumed. Another way that it could end is if your bromine dot reacts with the alkyl radical, but that's actually not an ending the reaction kind of step. It's a let's make more product kind of step. Yes, it's a termination reaction in that the radicals are quenched, but it doesn't end the reaction per se. An obvious termination step would be a recombination of the two bromine radicals. That's just a reverse of the initiation step. There are a multitude of different possible termination steps. Important notes for this reaction. The book stresses this, I will too. This really only works for bromination and chlorination. Iodine, far too unreactive, and fluorine, kind of the other end of the spectrum. You will see for yourself just why you might want to run away from fluorine chemistry by checking out this YouTube video. Very instructive. And, as I've alluded, there's a lot of selectivity issues with this reaction. So if, for example, I was going to look at this isoamyl pentane, ooh boy, let's see, let's give it the IUPAC name, 2-methyl-butane. That's better. Well, alright, I'm going to undergo free radical halogenation. I'll add bromine or chlorine, a little light or a little heat, and first selectivity issue is this one, as I've already alluded to on the first slide. You can get monohalogenation or dihalogenation or tri or tetra, etc. So to control that, the best way to control that is to have an excess of your alkane, and then it's much more likely that your halogen will react with alkane rather than your product. So that's selectivity issue number one. But selectivity issue number two, even with the monosubstitute alkane, I could get a really messy mixture because there's 4 possible isomers. So you should think about that. What 4 isomers could be formed, and which of them are chiral? So monohalogenation selectivity actually is an interesting topic in this chapter, because it turns out that for bromine, if I were to halogenate that 2-methyl-butane, I get almost exclusively the tertiary product when I use bromine. Whereas if I were using chlorine, I get, this would be a major product, but there would be plenty of some other products too. I don't get nearly the kind of exclusive product mixture. So why would that be? Well, this is a nice topic, as I said, because it takes us back into Gen Chem and thermodynamics. I'm going to illustrate by looking at 2-methylpropane instead. A little bit simpler because it's just the tertiary hydrogen versus the primary hydrogens. And we're going to focus on abstraction of this tertiary hydrogen. So this is actually, this hydrogen atom extraction step is the step where the product selectivity is determined. So if you look at the heat of formation for 2-methylpropane, you'll see it's 381 kilojoules per mole. And you compare that to the heat of formation of the acid that's formed, HCl or HBr. So what? Well, what is that? For HCl, comparing these two heats of formation, you can see that you get a lot more energy given off in the product side, making this an exothermic step. Whereas for HBr formation, you do not get as much energy given off, making it an endothermic step. So what? Well, so what is that in the looking at the activated complex at the transition state in this step. So here's our reaction coordinate. Our starting materials are the bromine radical and 2-methylpropane. Because this is an endothermic step when we're using bromine, the species right here at the transition state has mostly broken that carbon-hydrogen bond, and the hydrogen-bromine bond is almost completely formed. So what? So what that means is that it's clear in this structure at this transition state there's a ton of radical character on the carbon in this structure. Well, a corollary is that there's little radical character on the bromine. So to make it kind of obvious, the stability of Br dot versus Cl dot, not a huge difference. But we've already seen that there's a really big difference between a tertiary radical, a secondary radical, and a primary radical in terms of stability. So when it comes to radical stability and plucking off a hydrogen, if that Br dot was going to pluck off a primary hydrogen, whoa Nelly, that would be a much bigger energy of activation. Much slower, lots of selectivity in the bromination reaction. The difference, if this were chlorine, wouldn't be there because it wouldn't be this endothermic reaction step, and there wouldn't be a buildup of radical character in that structure. So, bottom line, you get lots of selectivity with bromination, next to no selectivity, well, little selectivity with chlorination. Here's what it looks like. Goodness gracious, look at that difference. 19,000 to 1 for bromination, only 6 to 1 for chlorination. Pretty impressive. Okay, so that's the introduction to free radical halogenation of alkanes. The next video talks about something that's kind of confusing. What happens when we throw an alkene into the mix? And just keep reviewing, and we'll do some problems in class, and we'll try to keep this all straight. See you in class.